Greetings, fellow pre-calcers. Today we're going to finish up with the third of our conic sections. So far we've looked at circles, ellipses, and today we're going to look at hyperbolas. This is the third that we're going to have. We're going to skip through parabolas. You've spent enough time on parabolas in past years that, oh well, we're not going to really miss anything there. So hope everybody's enjoying the nice weather that you have. Listening to the weatherman for the people. It is definitely a beautiful day out there. Hopefully you got a chance to take a listen to his broadcast on the GHS homepage. Otherwise, here, gearing up towards spring break, got palm trees. Yeah, house plants outside just to kind of deal with it. Anyways, let's get down to some math. I'm going to go over to my notes section. You should be taking notes as well, following along with what we've got, so that you've got this worked through and you can follow the examples. If you're just watching the videos, probably not going to work too well. So try it out, follow along with what we've got, and we're going to go from there. So we've been talking our conic sections thus far. We've got a circle. Circle, straightforward, easy, set of all points equidistant from a center point. We took that, we expanded upon it, and created an ellipse, which is a set of all points, the sum of distances from the two foci. Each focus point is constant. Now I'm going to go into Desmos and take a look at some things, see how we transfer from a circle to an ellipse, and then we're going to get this third conic section, our hyperbola. So I'm going to go over to Desmos. Is that the one I want? That is not it. Here's the one I want. So top left-hand corner, we've got the standard equation of a circle, x minus h over a plus y minus k squared over b. Now here I've got a and b. In our equations we've got a squared, b squared. Doesn't matter. I'm just writing it as a, b. You'll see why in a moment. Now if we multiply through, then we would have it equal to r squared, which is our radius. That gives us a circle. A circle is a special equation of an ellipse, which is why this can look so similar. Now we took this, we turned this into an ellipse by taking that horizontal and those vertical dilations and we made them different. So here, I'm going to use my slider to stretch that out. And so if we change our denominators there, we've got a stretch horizontal, we've got a stretch vertical, and playing between those two, if our b value is greater than the a value, we have a vertical ellipse. If our a value is greater than our b value, we've got a horizontal ellipse. And so we can see the play between those a and b values and see how they give us the stretch for our ellipse. The other sliders I have in there, we've got our shifts, left, right, up, down. I'll open up this file so that you have it available to play with on your own. Now with our ellipse, what I'm going to do is I'm going to take those foci and I'm going to stretch them as far as possible towards the edges there. So I'm going to take them from the center where the denominators would be the same. We have a circle. I'm going to stretch them out. Stretch, 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 stretch. Uh-oh. And then it breaks through on the other side. So in a way, if I take my ellipse and I take the two focus points, the foci, and we stretch them away from the center until they're the same distance away as the horizontal stretch, but then they can pop through the other side, we have kind of an inverted, an inside-out ellipse. Our focus points are now on the outside, away from the center. This graph is what we call a hyperbola. Now we've got these diagonal purple dashed lines in here. Those are asymptotes. Now an asymptote is an imaginary line to which we get arbitrarily close to, but without actually touching. We can drag around and we see that we're very, very close to those asymptotes, just not quite there. Now the play between the a and the b values, if our foci, the two black dots there, are really close to our vertices, we have this really tight hyperbola. As we get further and further away, we can see that our hyperbolas are stretched out. Our asymptotes are rather steep. Now, why does this make sense? Well, when we had our focus points inside, notice that our a value is 3 here, our b value, I've got 3 when our a and b are exactly the same. Then we have a circle. A or B are different. We're going to have an ellipse, either horizontal or vertical. I'm going to take that, happened, it popped out the other side as soon as we made the B value negative. So thinking back to the equation, Now this is why I don't have it a squared and b squared. I'm allowing for that b to be negative. We're going to have x minus h squared over some a squared. It's just that a squared is 3. This is going to be minus now, this y minus k over b squared. So when we have that subtraction, what happens is we have a horizontal hyperbola, this pair of curves that opens left and right. I'm going to put that back to our ellipse. If instead we stretch our foci out vertically, we've got a vertical ellipse and then pooh, pops out the other side, we've got a set of curves, a pair of curves that gives us a vertical hyperbola. Now notice here that this a value is negative, so the whole x term is negative. The y term is positive, the x term is negative. Same idea where we have a really thin, narrow hyperbola to a wider hyperbola, but the x term is negative versus the y term. And so you can play and see the center is always the same. Our vertex points just shift from our ellipse, the same idea as the ellipse, but those focus points are outside. Now geometrically what happens is our hyperbola is actually the set of all points such that the difference of distances from each focus is constant. So rather than adding the distance from the foci and getting it the same as with the ellipse, we have now the difference is going to be the same for each. Before, we had the standard equation of an ellipse. Now we get the standard equation of an hyperbola. Very, very similar. Just notice that I've switched from being addition between the x and the y terms to subtraction in the x or y terms. As we saw just in the Desmos demonstration, if the x is positive and the y is negative, we have a horizontal hyperbola. If the x is negative and the y is positive, really I'm going to reverse those two. Now notice that I am keeping the b value below the y, the a value below the x, just to keep that consistent. So if we have the x is positive, the y is negative, then we're going to have a horizontal hyperbola. If the y value is positive, the x value is negative, we're going to have a vertical hyperbola. Now, just like before, our center point is that hk, the left-right shift, up-down shift. Putting in writing what I've got, my hyperbola is horizontal. If the x term is positive, the y term is negative. We have a vertical hyperbola if the y term is positive and the x term is negative. That's the one on the right. Horizontal, distance to the horizontal vertices, the a value, just like with the ellipses. If we're vertical, the distance to the vertical vertices is that b value, just like with ellipses. Now, something that changes between ellipses and hyperbolas. Now, before an ellipse, it's the sum of distances. Our distance focus was that a squared subtract b squared. Now it's the difference between distances. What happens, there we go. The distance of the focus is c squared equals a squared plus b squared. It is now the Pythagorean theorem. The signs have swapped from the ellipse, and that's one of the key things because we want the distance to be further away than the vertices from the center. Pulling everything into a table, keeping it organized, we have what's called the transverse axis. The transverse axis is between the vertices. Now going back to our hyperbolas, we are going to have an axis between vertices, but there is nothing here you can see left or right. The transverse axis is the distance between two vertices. Here we would have a vertical transverse axis. If I make the y term negative, we would have a horizontal transverse axis. That's just the name that we give to it. There is something in the opposite direction. We're not going to concern ourselves with it at this point. You might see it in another class. Pulling everything together, our hyperbola is horizontal if the x term is positive, the y term is negative. Our hyperbola is vertical if the y term is positive and the x term is negative. The transverse axis, the distance between vertices horizontally would be 2a. Distance vertically would be 2b. So that a, the denominator of the x terms, is our left-right stretch. B is the distance vertically is our up-down stretch. So it makes sense that our center, if we have a horizontal hyperbola, we're going to add or subtract that a value to get that horizontal change. We're going to have hk plus or minus b if we've got that vertical change. Now what you notice in the graphs, we have these asymptotes here. Those asymptotes come out It's a combination of the horizontal and vertical stretch. From the center point, you can see our two asymptotes intersect at the center point. The slopes of those two asymptotes are going to be plus or minus b over a for both. Now b over a, that is the y stretch over the x stretch. It's the same thing as all the way through. Slope is the y over the x. Foci, once we find c up above, foci, we've got h plus or minus ck, or hk plus or minus c. It's, again, that distance from the center. So that we find that c value, go to that distance from the center. We're going to take a look at two different examples, one written out, and then the other we're going to need to complete the square so we can follow along. I'm going to change windows here. Now in this case, I have an a hyperbola written in standard equation. We notice by looking at this, we have a hyperbola and not an ellipse because we are subtracting between the x and the y terms. Just like before, we can easily identify the center. We look at the shifts left, right, and up, down. I've got 3, -1. I can tell that the hyperbola is horizontal because the x term is positive, the y term is negative. That's the piece being subtracted. If x is positive, we're horizontal. If y is positive, we would be vertical. We find the a value, our denominator for the x, is going to be 2. Our b value, the denominator for the y, is going to be 5. From there, we can use the center to find the transverse axis vertices. It's going to be left and right this time. 2, because this is a squared equals 4. Notice the y stays the same, and I've written those out. We can find the distance to the focus between the equation. So the c squared equals 4 plus 25. That is the sum of the two denominators, and c is the square root of that. So our foci are going to be the center point. Since we're horizontal because the x is positive, we're going to add and subtract that square root of 29, that c value. From there, our asymptotes we can find is the b value 5 over the a value 2. We've got our asymptotes. I'm going to go to Desmos, plot this all out so that we can see it done out. Now, how I would graph this as well. Now, going through, we've got our center point there. I'm going to go through, plot my coordinate that I have. We know that this is a horizontal hyperbola, so that I can plot my two horizontal vertices, with the left vertex and the right vertex there. I'm going to plot my focus points. I've got my left focus and my right focus. Don't want to do that. I want to turn off the labels. Now from here, I'm going to graph my asymptotes. The asymptotes, we know the slope, and we're going to take the slope from that point. So what I'm going to do is I'm going to sketch in a box of sorts. I'm going to draw the section between my two vertices there. And then I'm going to draw in a box. Now the distance that I have here is I'm going to go the y stretch vertically, the y stretch up vertically, and the y stretch down vertically. And I'm going to create a box using those a and the b values. So I've created a box. These would be the corner points of an ellipse. Notice the distance from the center horizontally is 2. The distance vertically from the center to the top of that box is 5. That comes from the a value and the b value. From there, I can use my box or my asymptotes. I will sketch in knowing the slope of the asymptotes. The hyperbola is going to hit that vertex point, and it's going to trace, get very, very close on either side to those asymptotes. I would sketch in my asymptotes there. The box is really just a guideline helping us identify the asymptotes. Otherwise, we've got our asymptotes sketched in, we've got our hyperbola passing through those vertex points. We've labeled our foci, we've got the center, we have our vertices. I'm going to take another example now. Now this is our hyperbola written in the standard equation form, where we've got the shifts and we've got the stylations, horizontal and vertical. Now we're going to look what happens if I give you something where it's not so easily written out. Back to the general equation. Now, we've seen this with the circles, with the ellipses. We need to complete the square first. So we're going to group the horizontal, the x terms. We're going to group the y terms. What I've done is I factored out the 25 from our y terms. I factored the 144 from our x terms. Setting up, we know that we need to add something to complete the square for the y term. We need to complete the square for the x trinomial. For the y, I'm going to add 9. Now notice that I've added 9 inside my trinomial, but this isn't just 9. This is actually 25 times 9, so I have that over on the right side. Think about what I need to add here. I'm going to add 4. But this is actually negative 144 multiplied by 4. So I've added in negative 144 multiplied by 4. I'm going to now factor, because those are now perfect squares since we completed the square. I'm going to combine these terms all together. Last piece that we want to turn this into the standard equation, I'm going to divide both sides by that 3600. I've now converted this into the standard equation of our hyperbola. Now we have this 144, this 25. Notice 25 multiplied by 144 gets us 3600. It worked out rather nice this time. From here, we're going to find our center. We know that our hyperbola is vertical because the y is positive, the x is negative. I can then find the a value and the b value. Notice b is the y dilation. A is still the x dilation. Since our hyperbola is vertical, we're going to go 12 units up and down from our center for our transverse axis vertices. I'm going to use that a and b to find the c value. Same idea as before, the Pythagorean theorem, c squared equals a squared plus b squared. I can find that the c is 13. And because, again, our hyperbola is vertical, we're going to go 13 units in either direction, up and down from the center. Finding me the location of the foci. Lastly, the asymptotes are going to be plus or minus b over a. It's the y dilation over the a dilation. We have our asymptotes plus or minus 12 over 5. We go back into Desmos, see how that looks, and we can compare. So here was our initial. We've got our center at negative 2, 3. We have our vertices. We have our foci. I'm going to graph in those asymptotes, just to show that our equation is exactly the same as the initial. Let's turn that off. Once we have those points in there, I can graph that and see that we are, in fact, exactly the same as the initial equation. We've taken it from general equation, where it's multiplied out, turned it into standard equation, or we can identify the parts. Try it out. Let me know if you've got any questions.